think we talked about this picture a little bit before, and one of the things I really think is important for you to understand in this study of the eyeball is to understand that there's basically 3 layers to the eyeball, 1, 2, 3, and I've written them over there. There's the fibrous layer, which is the very outside layer, and it's pretty simple. It consists of the sclera, which is the white part, and the cornea, which is the clear part in front, right? So that one's easy. The second one is the vascular layer, and the vascular layer is mainly, it's the choroid plexus, or choroid, not choroid plexus, the choroid layer around back here that supplies the blood and everything. But up front, you see this layer differentiates and becomes the these muscles. And this is called the ciliary body right here, which we haven't really talked about yet. It has 2 major functions. One is to pull on the lens in order to change the shape of the lens, and also it also is going to make the fluid that's in the eyeball. So we'll talk about that. And then notice that that same layer comes on up here and extends across in front of the lens as the pupil. And the iris, the iris is the muscle here, and the pupil is the space in the middle where the light comes through. So it changes sizes based on light that's wanting to go through there. And then the innermost layer, of course, is the retina. Now this is very confusing to a lot of students. They think, well, wait a minute, why is the retina on the inside? Well, you think about it, the light's going to come in here, and the thing you really want the light to do is hit the retina. So the retina is on the inside. It gets its support from underneath. It gets its blood supply from down below. And we'll talk about that more here in a second. So I just went through this, the choroid, the iris, the ciliary body. Those are the important parts of the vascular tunic. And obviously 2 of them don't have anything to do with vascular disease or vascular supply. Only the choroid does that part. Yeah?
So the eyeball is hollow so after the retina, right? And it's just filled with that jelly?
Yeah. Well, the back part, which we call the posterior cavity, is full of kind of jelly stuff. Yeah, vitreous humor. The front part is filled with water. It's called aqueous humor. And that's it. That makes sense?
Yeah.
Okay. Let's talk about the pupil for a minute. Please notice that the pupil has 2 sets of muscles in it. One is the dilators, these guys out here, which are actually radial in direction. See, they follow the radius of the circle here. So the pupillary dilators are a set of radial muscles, and when they contract, they pull the iris open, right? And the ones in the inner part here are the constrictors. They are a sphincter muscle. They close around it like this, and so when the constrictors contract, you see it pulls it in and makes the pupil smaller. Okay? So I think the main things you need to know are that, you've got 2 sets. One sympathetic, fight or flight, right? One parasympathetic, rest and digest. The ones that open your eye are these pupillary dilators, which are radial and they're on the outside. I'll just leave it at that. The ciliary body thing that we just talked about over right here in the front part of the vascular tunic, it ends posteriorly at this thing called the ora serrata. I think I mentioned that the other day. That's the back part of the ciliary processes and the ciliary muscles. And let's get to pictures here. And then behind that, it's the choroid. The choroid goes all the way around the eyeball and supplies the blood vessels to bring oxygen and nutrients to your retina. Clearly, if you don't have blood flow going to your retina, you can't see, because those neural receptors, which is basically what the retina is, need blood to work. Let's talk about the retina for a bit, and I suggest you read this area in your book quite carefully because the book is good. Everything I would tell you, I was just flipping through the book before coming in here today, is that there's some really good little clinical boxes. The little clinical boxes that talk about, one that talks about glaucoma, and one that talks about LASIK, and one that talks about vision and different problems. Cataracts, I think there's one. Read those. Those are fair game. I think they're very important that you understand what can go wrong with some of this stuff. And the book does a really nice job of presenting those things in concise, short fashion. Okay. So the neural tunic is the last layer we're going to talk about now. It's the one that's in blue over here on my wonderful drawing. And basically it has the neural parts, the retina, are the inside part. That's where the receptors are that sense light. And those are basically two types of photoreceptors called the rods and the cones. And you need to understand rods and cones. You need to understand the difference between them. And let me just describe it like this. If you get up in the middle of the night and you got to go to the bathroom and there's very, very little light in the room. Maybe there's a little bit of moonlight coming in through the window, but that's it. Now, these rods are what you see with in a situation like that. They are very, very sensitive to light. In other words, it takes the tiniest bit of light to fire them off. But also remember that when you're going to the bathroom in the middle of the night and it's very dim, you're not seeing in color. Okay? You're also not seeing very clearly. You can maybe make out the door and you can maybe make out the doorknob, but you can't see any of the subtleties of what's going on in your bedroom, right? You're just walking and it's dark and you can't discriminate very much at all. These are the rods, and they're the ones you use in the dark. Now that's the way the book has you try to remember that, is because they both have an R in it. Okay. On the other hand, in the morning when you wake up and the light and the bedroom is full of light, you need your cones, because your cones give you color and clarity. And they aren't near as sensitive. They require a lot more light to work. But when they do have the light, they can give you real good vision, and it's color vision, and it's very clear. Now, you might think, and you would be right if you thought that, well, most of the cones live around the fovea. The fovea, remember, is that main part of your eye that's looking straight out, also called the macula, which is where you do your best seeing. And because we have these wonderful eye muscles, we use our macula all the time, because we just move our eyes so we are using the best part of our eye all the time. Now try this. Pick a point. Everybody look at this N right up here on the board, okay? So stare right at the N, and now take your left hand, hold it straight out, and then bring it in, and wiggle your fingers, and tell me when you can see it. Okay? Don't move your eyes. Keep your eyes looking at the N. I've got to get it into about here before I can actually see my fingers wiggling. Now, can I make out my fingers when it's out here? No, I don't see it very clearly at all, but I can see there's something there and I can see there's something moving, okay? So that's what happens when you don't use the best part of your eye. So what would I do, of course? I would move my eyes over there and look at my fingers, and then I would see them very clearly. That's the difference between the central part of your eyeball, your macula, your fovea, and the rest of your eye. Okay, so keep that in mind. And indeed, this is the fovea right here. Notice it comes straight back here, and the fovea is located just lateral to your disc. Now, there's a test in your book, and we have a little test cards over in the lab, and I want you to find your blind spot today in lab. And it's really simple, because if I cover up my left eye here so I can't see it at all, see through it at all, and I look straight ahead, that's my fovea looking right there. So where would my blind spot be? Well, it would be right about out here. And indeed, if you keep looking at that and move your hand around, you'll find a place out here where it'll go away. You can't see it. Why is that? Because you're trying to see with your disc here. And the disc doesn't have any, it's not retina. It doesn't have any photoreceptors. What the disc is where all of these little nerves that come from the retina all around the eyeball, they work their way over here, and then they turn and take a turn out the back and go out as the optic nerve. Okay? So you do have a blind spot. Now, our brain doesn't really like looking at blind spots, so it just kind of ignores it most of the time. And if something's sitting in the blind spot, we're going to just move our eyes automatically so that we can see it. Okay? So you really have to kind of test for it like that. Here's what the disc looks like from the side. You see that all of these nerve fibers here, these are all axons that are coming from these cells. We'll talk about these different cells in a minute of the retina. But they all send their nerve fibers to the back of the eye, to the disc, and then back out they go. They go to the optic chiasm, and they're going to eventually go on up to the brain, which we'll see in just a minute. Now remember, here's the sclera, which is the fibrous layer. Here is the choroid layer, illustrated in that little brown layer right there. And then here's the retina up here. Okay, the neural tunic is in front. When you look into the eye, which we will do because we have a bunch of ophthalmoscopes over in the lab, this is what you'll see. This is the disc, so this is the blind spot actually, and this is the fovea or the macula over here. So when we talk about macular degeneration in old people, this is the area of the retina that is kind of given out on them. Now, you notice that one thing is for sure, the macula doesn't have any of these big blood vessels running right through it. Because if they did, those big blood vessels would interfere with the light getting back to the retina. So keep that in mind. Okay, let's talk about the different cells that are in the retina, because these are the cells that let us see. Okay? Basically, there's the neurons of the rods and cones, and the rods and cones synapse with the ganglion cells. I think there's a couple of diagrams, and I was just reading through this before I came in here today. It's really handled very well in the book, so be sure and read through this part. Then there's the horizontal cells, which extend across the outer portion of the retina, and the amacrine cells. Let's go to a picture here, because I don't like dealing with non-pictures. I'm a picture guy. All right, here is the retina. This is the picture that I think you really need to know right here. First of all, here's the rods and cones right here. They draw the blue ones as cones and the others as rods here. Remember that there are more cones around the macula than there are anywhere else. And there's percentages given in your book, which you don't need to know, but I think there's a lot more rods in your eye than there are cones. So, this is the confusing part. Everybody look up here for a second, Because see, here's the rods and cones. This is the outside of the eyeball, okay? Now how do you see? Well, the light, which is coming in from the front of your eyeball, see this little arrow here says light? That's the way the light comes into your eye. And notice that the light goes through these blood vessels. It goes through all of these fibers that are going back to the optic disc to get out of the eye. Then it goes through these cells called the ganglion cells. Then it goes through these cells called the bipolar cells. You see there's some other cells here called the amacrine cells that help process the vision a little bit. And then there's these others called the horizontal cells, which kind of hook a bunch of rods and cones together. And then finally the light goes back here to the rods and cones, which is where you see it. These are the cells up here that respond to light. So by the time the light gets to the cells that are actually going to see the light, it's already passed through all this other stuff. Now you may ask yourself, well, wait a minute. I'm looking here at that white wall over there and I don't see any blood vessels running through my eye, do I? Right? But yet, the light has already passed through all those things. Well, why does your brain just suppresses those visions? Because you can actually see the blood vessels, but you don't, because your brain has been looking at them your whole life. Those blood vessels have been in the same place every day your whole life, and the brain has gotten used to that, and it just kind of filters those out. Okay? And clearly, at your macula, there aren't any blood vessels running through there, because that's where you're going to do your best vision anyway. Yes?
So the first thing, the first place that the light goes in the blood vessels?
Say that again?
The first place that the light go is in the blood vessels, right?
Well, the light has already traveled through your stuff in front, the cornea, the conjunctiva, the cornea, the anterior chamber, the lens, come back through the vitreous cavity, and at the very back of the eyeball, this is the first thing it hits. Yes. It's traveled through all those other things, though, too. Yeah.
It's the concept with the fan and the projector. It's constantly there, so your brain just
Your brain suppresses it, exactly.
I have a question.
Yeah.
So, I just had an eye test, and the lady said that I was very sensitive to the light because I kept
Blinking?
Yeah. Does that mean I have more rods than I do cones? Or because I've always heard people with darker colored eyes aren't as sensitive to the light, where hazel colored people are.
I'd be BSing you if I answered it, so I don't know the answer. Some people are just more sensitive to the light.
Like I've heard the light color thing too, though, that dark eyes versus light.
Well, we will talk about. Yeah, that is a point. Yeah.
So when you have the floaters, is that like sloughing off of the cells of that outer?
Is floaters really things floating around in your
But is
eye?
it like sloughing off of cells?
No, they're usually from up front.
Like,
My understanding is they're from up in the anterior chamber, front of your eye. All right, now to help understand that the point you just made, which is really good. So let's think about this. If this back of your eye back here was really light colored, and the light came in here, and it hit a really light thing back there, what would happen to it? It would bounce all around, right? If it was mirrored, it would reflect off, right? But if it's light colored, the light would bounce around. Well, that would confuse you, because the light would bounce the front of the eye, off the back of the eye, and things like that, and give you these weird pictures. So what the eye has done is it's created this very dark pigmented part of the retina back here. The very back layer is a layer we call the pigmented layer, and the idea is that any light that gets all the way through, it gets absorbed and goes away. It doesn't bounce around, so you don't have to see it again. Okay? Now, some people I'm sure have darker pigmented layers than others, and so therefore they would be a little bit different in their reaction to light. Yes?
So the pigment absorbs the light?
Yes. This is what it looks like under the microscope. This diagram right here looks like this over here. And we have cuts of eyeballs down there that you can look at under the microscope, and be sure you look at those. This is important. Now, the biggest problem that students have is when they look at one of these cuts, they think that's the front of the eye up there, but it's not. I mean, this is the front of the eye here. The light is coming in this way. So you need to know when you look at a cut through the eye, which way is which, right? So know enough about it to know that. I'll probably ask you, which way does the light come in? All right, let's go up here and talk a little bit about the chambers of the eye a little bit more. The big posterior cavity is also called the vitreous chamber back here in back. The smaller anterior cavity up here in front is divided into two chambers, sort of. They're not really separate, but it is two chambers. The first one is called the anterior chamber, and it goes from the cornea up here in front to the lens. Excuse me, to the iris. And then the posterior chamber goes from the iris, which I've drawn here as a red line, back to the lens. Now you notice that there's a big opening in between there, which is your pupil, right? Which is open, completely open. So they are connected, and don't get that confused. All right, so what's in this smaller chamber up here in front? It's called aqueous humor. It's just the fluid inside of your eye. What happens with it is created right here in this muscular layer right here called the ciliary body, and it's secreted out here into the anterior chamber. Actually the posterior chamber right there, and then it percolates around and comes up here through the iris pupil, and it comes around here, and it comes over to this corner, and it passes into what I think is one of the greatest names in the world. There's a little canal right in here, right in the front edge of your cornea up there, which is called the canal of Schlemm. Isn't that a great name? The canal of Schlemm. And the canal of Schlemm is what takes the water, the aqueous humor, out of your eye and puts it back into your bloodstream. Okay? So, aqueous humor is formed in the ciliary body over here with these muscles, and it's secreted, and it comes out here, and it should go into the canal of Schlemm and leave. Now, why do we need intraocular pressure? Well, we want our eye to stay round, and it would kind of be like trying to play with a basketball that had lost half of its air and was out of shape, right? And you need it to be in shape so that everything focuses just right. And so intraocular pressure is very important. If something happened out here to the canal of Schlemm and it got clogged up, your ciliary body wouldn't get the message, and it would keep making fluid, and therefore the fluid in your eye would build up, and the pressure would build up, and when the pressure in your eye builds up, we call that
Eye pressure.
glaucoma.
Okay.
But that was a great guess. God, you would have gotten full credit for that. Just kidding.
Oh.
Okay. Now, this seems kind of weird, but if you take your finger out here and go out on the side of your eye and push in, we call that blotting the eye. It's kind of like if you pushed on a basketball. You can actually push it in a little bit. Same with this, you can blot it. But I can tell you that if you ever feel the eye of a patient who has glaucoma, it's like pushing on a rock. The eyeball is totally tight. It doesn't push in at all. So you really can tell the difference in intraocular pressure with your finger. Now, we have much more sophisticated ways to do it now. The way it's usually done now is actually with a puff of air. The puff of air pushes in on the eye, and then a
Worst eye test ever.
ultrasound thing.
Pilots hate
Oh no, that's not as that's much better than it used to be. They used to actually put a little weight on your eyeball and see how much it pushed in. To do that, you had to numb up your eye and all this stuff. So it was a big deal.
Because I had to do that exam on pilots and flight crew when I was in. It sucks.
So remember, when you're learning this stuff, there's a difference between cavities. There's an anterior and posterior cavity, and there's an anterior and posterior chamber. Both of the chambers are portions of the anterior cavity, is the point. But just be sure you don't get screwed up by that, because that'll be in questions, and you'll have to understand those terms. Okay, so back here, here's the circulation of the aqueous humor. I said this is the vascular tunic right here, and remember it has muscles in it. The choroid kind of differentiates into these muscles, which are called the ciliary body. This is where the fluid is made. It comes out into here, goes into the back cavity as well as the front. And then from the front, it goes across here in the posterior chamber, right? Posterior chamber comes out through the pupil into the anterior chamber, works its way across through the anterior chamber, and lo and behold, over here at the corneal limbus, remember where the colored part of your eye turns into the white part of your eye, right here at this point. That's where the canal of Schlemm is located that carries the fluid out. All right, I'm going to use this picture here to describe an important point, I think. You notice that the lens is right here, and notice that there are these fibers that go out here, that go to the lens, and they're called the suspensory ligaments. Okay? Now, we talked a little bit earlier about how if you wanted to see things up close, you would want a really thick lens. And if you wanted to see things that were a long distance apart, you'd want a really thin lens. And indeed, that's the way it works. Now, how are you going to remember that? Well, here's the way I remember it. When I was a kid, my dad was in the Navy, so we would travel across the country going home to grandparents' houses a couple times a year. And it's usually a 3-day trip in the car. And it was crazy. But I would read a lot. And I'd be sitting there reading in a book, and I would say, "Mom, my eyes are so tired, my eyes hurt." And Mom would say, "What?" What would Mom say at that point?
Look down.
Stop reading, yeah. What else?
Look out the window.
Look out the window. Look at something a long ways away, okay? Because the point is, in order for these muscles, in order for your eye to focus on things close, the muscles go around your lens and they squeeze down in order to make the lens bulge out and get thicker so that you can see things that are close up. Point being that the muscles are activated when you're looking at things close up. The muscles are activated when you thicken your lens, make it thicker so you can see things that are up close. And when you look at things that are far away, the reason your eyes feel rested is because all those muscles can relax. And when they relax, the lens pops back to its normal shape, which is thin. The point being, these muscles, you would think the way they work is they pull this way to stretch the lens out, but that's not really right. What happens is they contract, but these muscles are circumferential, they're going around, and when they contract, they pull in, they squeeze it in, which then makes the lens get wider. You got that? If you don't, read through it in your book. because there will be questions that will address that. You know, when is the suspensory ligaments, when is the ciliary body contracting? What shape is your lens when you're looking at things far away? What shape is your lens when you're looking at things up close? Okay? And that's the way I always remember it, is because when I'm looking at things up close, that is when the muscles are contracting, because that's when my eyes used to get tired. Yes?
So just to be clear, so when the ciliary body contracts, it pushes the suspensory ligament in, which pushes the lens, makes it thicker, right?
And it lets it get, yeah.
Yeah.
It has a natural elastic tendency to be thick.
So it's that action of the ciliary body that's creating.
Yes, the ciliary body is what controls the shape of the lens. And that's why I can look at that guy out there walking down the sidewalk and then look at my finger right up there up close. And my lens has changed shape a lot, but it does it very quickly. Okay? Okay, the posterior chamber, the big one in back, is a thing full of jelly. All it's there for is just to support the eye, to keep the eye nice and round, and to support the retina. It's needed, the vitreous is needed to push the retina up against the wall of the eyeball to keep it in shape, to keep it flat. The lens is a pretty cool structure because not only is it clear that you can see through, but it also can change shape. Think about that. We don't have a lens that we can use that just changes shape, right? And yet it changes shape thousands of times a day, but yet it stays clear. The little crystals that are in there are called crystallines. They provide clarity, they provide focusing, but they allow the lens to change shape. When the lens, which is right here, of course, when it gets cloudy, that is called a
Cataract.
not a cloudy eye.
Well, it says it right here. Cataract.
Okay, yeah, that's called a cataract. Yeah,
Also a cloudy eye.
yeah. Okay, now we're going to talk a little bit about light and how light travels from the side of that building over there. Where I'm looking at the side of that building. How does that light travel to get to my eye? And I threw this picture in of Josie with goggles on because she used to be a speed swimmer, racer. And why? I'm sure most of you have worn goggles or a diving mask. Why do you wear that? What?
So when you're under the water, and you can open your eyes and the water is getting in your eyes and removing the fluid within your eye.
So you can see where you're going.
You can see. So why can you see with goggles on, but you can't see if you just are in the water and you open your eyes in the water? Yeah.
Light travels differently through air than it does through water.
Light travels differently through air than it does through water. That's right. And you know what we call that?
Refraction.
We call that refraction. That's right. So no one can jump in a swimming pool and open their eyes underwater and see clearly. Why is that? Well, it's because you've spent your whole life with your eyeball exposed to air, and you've become used to the refraction that happens when light goes from air to cornea to water to get back into your eye, right? Whereas when you are touching water, it changes all of that because it refracts differently. Now, you're probably thinking, oh, that's bull. Well, look at this. Look at that picture right there. That is refraction. Now, what do you see?
Distortion of the spoon.
The spoon isn't exactly straight, is it? It looks like it's coming up here, and then it takes a break and goes over here and goes up there, right? Now, what's the difference? Well, the difference is exactly the same as with those goggles. because this, to see this part of the spoon, it has to go through air, then the glass of the glass, then the other side of the glass to the water, into the water, and then eventually and come back through all those different layers as well. So it refracts at each interface. And you notice the one on top refracts differently because there is no water up here. Yes?
Is it the same thing with like heat waves too? When you're looking down like on a hot day, looking down a road and the road looks distorted?
I don't know. I don't know what makes that happen. You know? Is that what it is? It's heat waves.
It's the heat has a different density than the
Yes,
not
that's
hot
it.
air, and so the light waves wiggle as it goes through the
Yeah.
different densities.
Thank you. I could have said that. I just didn't want to be BSing them too bad. I like to BS them sometimes, though. It's good. All right, so here we go. The lens is what's going to handle our light refraction, and basically our lens is what is going to focus for us. So understand the term refraction. Refraction is the bending of light in anything when it goes from one density of stuff to another. Okay? So the main refraction point in our vision, I have to tell you, this is a point to remember. The main refraction point is at the air to cornea surface on the outside. Okay? And that's why the swimming goggles are so important, because without goggles, you just can't see clearly underwater at all. Okay? Now, usually y'all give me the answer when I say, well, why do you wear swim goggles? Everybody says, well, it's to keep the chlorine out.
No. It's not the chlorine that makes your eyes burn, it's all the gross germs and skin particles in there.
No, it's the chlorine because it affects the pH.
It's the pH. Yeah.
Because it
that's-
makes something more.
It's also all the other
Yeah. All right. Well, anyway.
It affects the pH.
All right. Let's talk about this this stuff here. Let's talk about a couple other points that you need to understand in order to understand light. The focal point. It's the specific point on the intersection on the retina. Focal distance is the distance. Let me show you some pictures that will make that more clear. We got to go through a couple more words before we get to the pictures, though. Accommodation. You've got to know what accommodation is. Accommodation is what your lens does to focus on things at a different level. So I'm looking at the clock in the back, and my lens is accommodated to that so that it's crystal clear. Then I look up here at my finger, and my lens accommodates to this. So accommodation is the process by which your lens changes shapes. It gets thicker or thinner in order to keep things focused on your retina. Keep them nice and sharp on your retina so you can see clearly. Astigmatism. Anybody have astigmatism? And did they fix it? Fix it with your glasses?
With my contacts, yeah, I have a higher contact power in the left than I do in the right.
Okay. Well, that's not what astigmatism is. Astigmatism is, we would like to all think that our lenses are nice and round and equal all the way around, right? That would be a nice thing to think, but ladies and gentlemen, it doesn't work that way. Many of us have our lenses that are bent a little bit. They're creased. Now that crease may go up and down, it may go out to the side, it may go this way. But an astigmatism is a misshape of your lens. And because of that, it doesn't bring the light in perfect. It misshapes it. Now, clearly there didn't used to be any way to fix that. If you had astigmatism, you were just out of luck. But in these modern days, with the incredible computer-guided lens grinders that we have, that we can make, we can actually fix for a misshaping of your eye by changing the lens to correct that. That's what astigmatism is. And let's talk about visual acuity. Oh my goodness. All right, I want you all to understand this, okay? And to make you understand it, I'm going to walk around up here a little bit and show you that, well, what's normal vision?
2020.
2020. Okay, now what does 2020 mean?
But you can see well.
Perfectly.
Yeah, but what does the 20 and the 20 mean?
Oh, it's
Isn't it a distance?
A distance, yeah. What's the units?
Feet.
Feet, yeah. Okay. All right, so here's my eye chart up there, and I am 20 feet away from it, okay? And I have normal vision with my glasses on, and so I can see everything perfect from 20 feet right here, okay? So you would say that I have 20/20 vision, okay? Now, some of you guys out there have really young eyes, okay? And so you have really good vision. What might really good vision be?
2010.
2010. Good. So when the numbers get smaller, 2012, 28, 2015, that means you can see even better than the average Joe, okay? So what does that mean in terms of the eye chart?
Where you can see normally at this distance, they can see it the exact same, but farther back.
No, it's, yeah. It's like if you can see it at 20 feet, they can see it at 30 feet. Sorry.
Well, why would they lower the number to 10?
Because you can see it 10 feet back. Because if you can see it at 20 feet, like if you can see it at 20 feet, with the deficit of 10 feet, he can still see it.
Yeah, I can't remember. It's been like 2 years since I actually went over this.
Quit holding out on us.
Anybody? Anybody?
I know this.
Is it that you, where you have to be at 10 feet
Yeah.
to see that they can see at 20?
Exactly.
Yeah.
So the normal guy
Yeah.
would have to go up here to 10 feet, which is me, and I can see it perfectly clear from here, but they can see it perfectly clear from here at 20 because their eyes are better than normal, right? So, what's the definition of blindness? For driving a car, the definition of blindness, I believe, is 20/80 or 20/120, something like that. So think about that. What does that mean? 20/100, let's just say. Huh? That means they can't see for shit. Right. Okay. Here you go. Somebody that's 20/100 can stand here at 20 feet and see it, but a normal person with normal eyes could go all the way back here to 100 feet and still see it perfectly well. Okay? Got it?
Got it.
So 20/20 is normal, 20/10 is better than normal, and 20/200 is worse than normal. Okay?
I'm not raising my hand. I'm
You got it?
just
Okay. Okay, you all got that? Don't forget it. That's one thing you'll want to know. All right. Now, how does this light, we're talking about light waves, but you guys are just, could care less about that. You just want to know, why can I see or why can't I see, right? So think about it like this. This is a normal eye right here. This is the definition of accommodation. But this is a normal eye, okay? And so if I'm looking at something close, like right here, okay, I can change the shape of my lens. It gets thicker, see? And because it's thicker, it bends the light more and brings it in to focus it right there. Whereas, if I'm looking at something way out in the distance, as illustrated here, the light is coming in and the light is very parallel, you see. And so I don't need that much accommodation here. You see my lens is a lot thinner here than it is up there, and it still focuses it perfectly on the back of your eye, which is what you want because it's the back of your eye where you're actually going to see it, right? That's where your retina is. It's going to interpret it for you. Okay. That's normal. That's normal. This is myopia. This is some of you who need glasses, okay? Including myself. So here now you're looking at something off in the distance and the lens stays kind of flat, and because it's kind of flat it focuses it up here, which is in front of the retina, okay? Because it's in front of the retina, those light waves keep traveling and they start spreading out again here on the back side of that, right? And so they arrive here on the retina and it's blurry because they're all boogered up, okay? On the other hand, the opposite of that, and I don't care if you know these words because I can't remember them myself.
Wasn't one far-sighted, one near-sighted?
Yeah.
Exactly right. If you can keep them straight, tell me how to keep them straight.
Do you know which one's the right now?
Huh?
Do you know which one's the right now?
No. All right. So anyway, this lens here is also abnormal. It's not accommodating properly. Notice the light coming in from far distance away is being bent, but it doesn't focus until it gets back here behind the retina. So that person's not seeing normal either. It's cloudy. Because you see, it's hitting the retina here, and it's not all hitting at the same spot. Some of it's hitting up there, some of it's hitting down there, and making for blurry vision. Okay? So how do we fix them? Well, we fix them with glasses, right? And glasses are nothing more than a lens that changes the amount of refraction on the light coming in. So here you go. For myopia, to correct it, you're going to put in a lens up here which is concave. See, it's kind of scooped out on one side, concave. Whereas if you're just the opposite, you're going to have a convex lens which sticks out, you see, which makes it converge right on the right spot. So there's one and there's the other. Okay? Yeah.
So I heard a rumor, I don't know if it's true or not, but when you're looking at something, not from your phobia, your peripheral vision is actually your brain just filling in everything else, kind of. It's there, but your brain, because your eyes,
You're suppressing it. Yeah. Just like the fan in the motor, right? Okay. This is the most common eye problem, hyperopia. And hyperopia is the most common form of hyperopia is actually called presbyopia. Presbyopia. Think Presbyterian, think that good old time religion, think old people. Old people all get presbyopia. Hello, I didn't used to have these until about 7 or 8 years ago, and now I have to have them to see anything up close. So this is your basic reader lenses to read up close, and you can actually take people and measure the distance they can focus at as they get older. In fact, if you go to a medical museum, you'll find these little things that actually have your age on a stick going out, and they could tell. As people get older, they start kind of reading like this and holding it farther out until they finally have to get readers. So here we go. This is an example of presbyopia. Notice that it takes a convex lens to straighten it out. All right, now let's talk for just a second about LASIK, because you guys have probably half of you have probably had it already. Did anybody have LASIK in the room? It tends to be folks about up in their 40s that get LASIK. But LASIK is done for this problem here.
What? I thought it was only done mainly for people that are nearsighted, which is the other one.
It may be. You know what?
But not
I don't know what
farsighted.
nearsighted
Nearsighted
means.
is the myro, the other one. And so I'm farsighted, so I can't get
You
that
can't
LASIK
get that.
surgery.
Yeah. Well, there's actually a new form of it coming out.
Which is
Let me just give you the basics as I understand them. I don't do eye surgery, and I haven't had LASIK. But let me tell you, a guy by the name of Jonathan Swift, who used to write novels and stuff back in the 1800s or something, and he made a comment that I think of every time I go to a nice restaurant, and it says, it took a brave man to eat the first oyster. Think about that, right? I mean, well, to me, it took the bravest man in the world to have the first LASIK. Okay? Because here's what LASIK is. It basically is you take their lens here. They don't have this lens here, but they need it. They're tired of it. And so you take their lens and you make a series of little cuts in the lens. About 20 cuts. And they only go in a millimeter or less. It's done with a laser now. It originally was done with a knife. They cut into the lens, and by cutting into the lens out here, it weakens the lens and allows the lens to bulge out a little bit. Once it bulges out, it changes the shape. This becomes a lens, this is a lens, and now it should be perfect, right? That's the way to do it. Yeah?
So over time with LASIK, doesn't it, your eyeball like goes back to normal somewhat?
I don't know the answer to that.
Because my dad got it and now his LASIK, like a while ago, and now his LASIK's starting to wear off.
Well, his eye is changing too. Yeah, I mean his lens in here is changing as well. So yeah, it wasn't unpredicted that it would require redoing after a number of years.
Yeah.
But here's why I say it took a very brave man, because when they first started doing them, they started making these cuts in the eye like it and weakening your cornea. What would it have been like if you'd have woken up one morning and your eye had kind of given way up front and all your juice out of your eyeball was laying on the pillow there beside you because your eyeball had just given way?
Why does it?
Well, it doesn't because they don't go down deep enough into it. That's it. They figured that one out. But I think you had been really brave. And I remember when guys started getting them when this was 15, 20 years ago. I thought, you are crazy to have an operation like that on your eye that's going to weaken your eye, that you don't know what the long-term results of it are. And then you have to ask yourself this question. Is wearing glasses a disease? Is it a medical condition for which you would undergo surgery and risk your life?
No, they're kind of cute.
So do you think insurance companies were going to pay for it? No, they weren't. Now, I don't know if they do now or not, but yeah.
So when you said they started this and they used a knife,
Yes.
how did it heal? How did the eye heal afterwards?
Well, remember your cornea doesn't have any vasculature to it, so it didn't bleed or anything. It just, yeah. Okay. I think I've talked about that already, the outer cones. Let's just spend a few minutes talking about the chemical reactions that occur in your eye when you see. Now, you know, we talked about those taste receptors and how they were chemoreceptors, and the chemical in the food would touch the taste bud and hook up with a receptor for that particular taste, and that was what happened. And the same thing in your nose. But in your eye, what kind of receptor is it? It's a light receptor, yeah. And so it basically is a response between a photon of light. Remember that from 7th grade science, maybe little packets of light. They shine into your eye and they cause a chemical reaction, okay? Well, here's the chemistry that you need to know for my class, and that is that the pigments that are important in vision are called rhodopsin. Now, rhodopsin is actually a combination of two chemicals, opsin and retinal. And where does retinal come from?
Retina?
No, it comes from vitamin A. And it finds its way to the retina. Okay? So retinal is this chemical. And so remember your mother used to tell you to eat something because it was good for your eyes?
Carrots.
Carrots.
13.
Australia orange.
Yeah. Well, that is true. That's where you get your vitamin A. Here's how it really works, and please don't memorize all of this. Just know that when a photon of light hits on this receptor cell, and this is either a rod or a cone, the light causes a change in this retinal. This is a cis retinal, and when a light beam hits it, it changes shapes and becomes a trans retinal. Okay? So there's a basic change in shape of this chemical that is there in your rod or cone. That, like every neural reaction, then causes some gates to open, causes some sodium to flow in. Eventually, you know what you're going to do. You're going to set up a action potential, right? And it's going to send a action potential off back to your brain that says, yeah, that's yellow or something. And so sure enough, that's what happens. There's cyclic GMP involved here, but please don't go memorizing it. These channels open and close very quickly, and they cause a change in the voltage. Remember the old voltage in the wall of nerve cells? And once it does that, it sends it releases it fires, and it comes down here, and it synapses. This cell here, which is the rod or the cone, sends a signal down here to the next series of cells. That's it. Okay, that's all you need to know in my chemistry segment. We have three different kinds of color receptors. Now, you guys can't see it, and this looks like a bunch of whiteness out here too, right? But I can tell you that if you were standing up here, what you would see is a whole bunch of little tiny dots, okay? And if you were to look over here, you would see that the dots are either red or they're blue. And if you looked over here, you'd see that they're mostly yellow. And it's a combination of dots that accounts for these colors. That's the same way we see color. We have red cones, we have blue cones, and we have green cones. By combining those three colors, we can see all of the colors. Now, for those of you who have ever hooked up a VCR, you notice that there's a plug that's called the RGB plug, right? You ever seen that? Or you might have three separate plugs. One's R, one's green, and one's blue, right? Because the way our televisions create color is the same way our eye does. The difference is, well, there's really not much difference. We have red cones, we have green cones, and we have blue cones, assuming we're not colorblind. Some people are colorblind. Males are much more frequently colorblind than women. And I believe the color blindness in men is usually red-green. I'm not positive. It's in your book. You probably ought to read that. Anyway, so this is how these things work. You see blue cones, green cones, red cones. Interpret these different wavelengths of light to different degrees. And then our brain puts them together and forms colors out of them. Color blindness is the ability to detect certain colors. We had an orthopedic surgeon out in the Dalles who was totally colorblind. And it always cracked me up because I gave a couple talks to the medical staff out there, and he would put his hand up and said, "Wait a minute, what colors are those things?" He said, I'm colorblind. He didn't have a clue when you show him colored graphs or things like that. Anyway. All right, so now how does the light, now we have stimulated a photoreceptor cell. We've stimulated a rod or a cone, okay? And it sends its messages out to the first round of cells is called the ganglion cells. Is that right? Yeah, amacrine cells kind of interact. Anyway, we'll keep going. Oh, here it is. It's the bipolar cells and then the ganglion cells. That's why I have these slides. They remind me of this stuff. So the visual pathway really begins at the rod or the cone, which is the photoreceptor, and it's going to eventually end up in the cerebral cortex. We see with our occipital lobe back here in the back of our brain. And it's going to cross two synapses before it even heads out of the eyeball and heads towards the brain. The first one is at the bipolar cell. The second one is at the ganglion cell. Those are all right there in that row of 3 cells in the retina. So read that over. I think it's key to understand that. We'll talk about a little bit more about the pathways in a minute. Can everybody read the number there? 27?
12.
Okay. We have some color vision testing books over in the lab. I think everybody ought to flip through them and make sure you're not really a little bit colorblind. It's about 20 pages. It takes about a minute. So, how does this visual data work? How does it get to the right place? Now think about it. I'm standing here and I'm looking out in front of me, and we want everything over there on that side of my visual field, okay? We want that all to go to this side of my brain. And everything that's out there, we want to go to this side of my brain. That's easier for me to interpret if we do it that way. And so that's the way it works. The left half arrives at the right occipital lobe, the right half ends up in the left occipital lobe. And the way it works to do that is because of the optic chiasm. And I think I've described this to you before somewhere, but let's go through it again. Let's divide the eyeball into a medial and lateral half. A medial and lateral half of the retina, okay? In other words, the lateral half of the retina, this part of your retina, sees out that way. In other words, it sees the medial half of your visual field. Okay? Same on this side. The lateral half of this retina looks out that way and sees the medial visual field on that side. Okay? As the lateral pieces of information come down, they do not cross over at the optic chiasm. So things that you're seeing out to your left end up coming to your right brain. Okay? And the same token over here, things that you're seeing out to your right come to your left brain. What about the rest of it? Well, the stuff in the middle, which is just the opposite sort of, because here's the medial retina, and what's it seeing? It's seeing stuff out lateral, okay? That stuff is going to cross over and go to the other side. Over here, the stuff that's seen by the medial half of this retina, which is actually the lateral visual field from this eye, is going to cross over and go to the other eye. So that everything you see out that way comes to this side, and everything that you see out that way comes to this side. And then your brain processes into a vision, and you get used to seeing things, and so you can recognize things. Yeah.
Okay, I don't know if this is too beyond our ability to ask, but so I see something with my cones and all that. Now, how does my brain interpret that into an image?
Well, how does your brain interpret the feeling of me feeling that thing there in my finger?
It's an action potential.
It's an action potential, but how do I know that's something smooth? It's because I've felt a whole lot of smooth things. The same way your vision, I mean, you're not born knowing that that's a face, you know? But it's only after you've looked at your mother's face about 1,000,000 times that you start to recognize that, oh, well, that's a pattern, that's a face. And remember, I think I told you the story with the baby and their hand. It takes them a long time to figure out that that's a hand. It takes them even longer to figure out that it's their hand. And it takes them even longer to figure out when they move that hand around that it changes the vision of it, right? So it's a matter of practicing these things millions of times that allows the patterns to be established that we can then recognize as a pattern. Field of vision, depth of vision. How do we see depth of vision? Basically because of the fact that we have two eyes and they're a little bit different. So this one looks at that thing over there and it looks at it from this point of view, and this eye looks at it from this point of view. And so I've got two images going back to my brain, and my brain has practiced this through the years too and is able to figure out how far things are away. Now here's another way to think of that, is if you take your finger and hold it out there in front of you and you focus both eyes on it and you gradually bring it in closer, 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 closer. How do I know that it's getting closer? It's getting bigger, that's one thing. And I have looked at my finger a lot of times in my life. But what else is happening?
The finite details are being a little more.
No.
Eye position.
Your eyes, that's right. Your eyes are coning in on it. And your brain knows where your eyeballs are because it knows how much tension is on your eye muscles, basically. And so, yes, as you get in closer, you know that you're getting cross-eyed almost. And that's how we tell depth of field. Now, can you get a driver's license if you only have one eye?
Yes.
Depends on how old you were when you went blind.
I've seen them give some questionable driver's licenses.
Well, of course they have. There's questionable everything out there. But the point being that the way we know that that car is 50 feet away versus 10 feet away is because of how much our eyes come in together. Now, if you went blind later in life in one eye, you've been able to tell depth of field for so many years that you can actually just do it by size. So they will let people with only one eye drive, usually in a kind of a limited fashion, like maybe not above 40 miles an hour or something. I don't know what they do, but yeah, that's how we get depth of field. I think I showed you these pictures at the beginning, and I'll show them to you again now that you know a little bit more about it. This is the hot, steamy eye of glaucoma, acute glaucoma. Notice how injected all these blood vessels are and how red that eye is as well.
I think maybe he's a baby of glaucoma medicine.
Maybe not, but maybe he doesn't know he has glaucoma. How would you know if you had glaucoma? Huh? It's usually halos around lights at night. If you're out at night and you see halos around all the lights, that's the first sign of glaucoma. Cataract. I think I've told you all the story about going down to Mexico to do surgery up in the mountains of surgery. I went taking an eye doctor with me, and he would take the cataract out of old people, many of whom had been completely blind for 30 years because they had no access to health care. And they would walk a long distance to come to this little clinic, and he would take the cataract out, and he would put a big bandage on it, and he would have them, they'd mostly just sleep out on the grass overnight. The next morning he would bring them back in the office and take their bandage off, and I can tell you, there's nothing I have ever seen in my medical career was more touching than having somebody see for the first time in 30 years. They were incredibly thankful because they could see perfectly. They had to wear glasses, they had to wear thick glasses, but they could see perfectly. And I'll never forget it. It was so cool. Cataracts is the #1 cause of blindness, I think, in the world. There's some infections in southern down near the equator that leads to a lot of blindness as well. So this is in the retina. This is macular degeneration, I believe. This is the macula out here. You notice there's clearly problems going on out there. Those cells are dying, and that's what you see when you look in their eye. This is a retinal detachment. This part of the retina is no longer, it's floated up away. It's got blood in here behind it. That person has lost all that vision. Most retinal detachments these days can be laid back down. They suck the blood out from behind them, flatten them back down, and then they use a laser to kind of like weld the retina back to the vascular layer and hold it down. Pink eye, infection, conjunctivitis. No, this is really a great one. Y'all see what's going on there?
Bleeding in the eye?
No.
Oh, there's fluid in the...
This is pus in the anterior chamber down there that's gone to the bottom. That's a uveitis. That's an infection in the eye, bacterial uveitis in the eye. That's a bad deal. But it's treatable with antibiotics. This is a sty. You ever get one of these, just so you know, you can probably treat these yourself. Just kind of grab your eyelid and take a little needle and just poke it. Don't poke yourself in the eye, but you can drain it. This is called a hordeolium, I think, and it's an infection of what gland lives up in here?
Lacrimal?
Yeah, chalazion, there you go, chalazion, that's the name of it. This is diabetic. These are little ruptured blood vessels here, little microaneurysms that diabetics get, little bleeds into their eye. They can also be zapped with lasers now to keep them under control. Strabismus. Okay, is this nearsightedness or farsightedness?
Farsighted. Far.
Nearsighted, it's far.
It's definitely far.
Okay, so we're about 50-50. That's good, that's farsightedness. And what's this one?
Here.
Oh. So that means when you're nearsighted, you can see things near.
That makes sense.
That makes sense.
Okay. Let's start the ear, because I'm really struggling. We're going to miss another class next week. Next Tuesday is SAC meeting. What do they call it? In service, yeah. I don't ever go to it because I just can't stand sitting there and listening to a bunch of adults argue like children over childish issues. I'm sorry, but teachers are terrible. And I just don't do it anymore. Anyway, let's talk about the ear real quickly. We'll get some of the basic anatomy down. Basically, starting on the outside, you have these things here, which are called auricles. Okay? Stand up.
Me?
Yes, you.
Why?
I'm going to give you a hearing test here.
Oh no.
Now close your eyes. Close your eyes and just stand there. Just stand there. Where am I now?
You're over there.
How did you know that?
Because it's more loud in this ear.
More loud in that ear.
Louder.
Louder. Anything else different? When I walk over here, which ear does it get to first?
My left.
It gets to that one. So there's actually a time delay before it gets to your other ear as well. There's two ways we can you can have a seat.
Thank you.
There's two ways we localize things. One is by the loudness and also by the time delay. And you thought it was just came from Dumbo, right? Okay. So the auricle, what does it do? It provides this directional sensitivity we were just talking about. It protects the opening of your ear canal, and it surrounds the entrance to your external acoustic meatus. You remember that from when we studied the skull, external acoustic meatus? The external acoustic meatus is the hole, your ear hole that goes down there, and it ends when it gets to your eardrum. Now, I'll bet every one of you has put a Q-tip in your ear, which you're not supposed to do, and pushed it down there a ways, and eventually you'll get to where it hurts, and that's when you're touching your eardrum, okay? The tympanic membrane or your eardrum is a thin, semi-transparent sheet, and it separates the external ear from your middle ear. In your ear, you have cerumen, which smells really bad, okay? And why does it smell really bad? To keep the bugs out. That's right. Bugs don't want to live in there either, much less your finger. So, yeah, this waxy material is called cerumen, and I'll just leave it at that. It also slows down the growth of bugs in your external acoustic meatus. Now, when you get an infection in your ear, it's usually caused by swimming. We call it swimmer's ear. It's an infection on the outside. Okay, it doesn't go past the tympanic membrane, the eardrum. And so you treat it with ear drops, right? Now let's see, would they be otic or ophthalmic? Otic drops. Yeah, don't ever put ophthalmic drops in your ear,
Optic.
and don't ever put otic drops in your eyes. These words do matter, don't they? Okay, then we get past the eardrum, and just on the other side of the eardrum are the three ossicles, the three bones in your ear called the malleus, incus, and stapes. And remember that the middle ear is a cavity inside which is filled with air. It is filled with air. And also remember that it communicates with the back of your mouth, the nasopharynx, remember? The eustachian tube. Here's a picture of it, and let me just give you this little last bit of info here. So here's the auricle, here's the ear, and here's the external acoustic meatus, and here's the tympanic membrane, and we have some otoscopes that you'll be able to look in each other's ears and actually see the eardrum, okay? And it's kind of cool if you've never seen it because it's just like right there. It's like not a big deal. But you got to have a little fancy light and a magnifying glass a little bit to look in there. So here's your inner ear, or excuse me, this is your middle ear. It's full of air, and please notice that it comes down here and connects into your nasopharynx. Now, how many of you have been on an airplane and you start to come down to land, and every baby on the plane starts screaming? Right? And you probably get a headache. You feel the pressure building up in your ears, right? And what do you do to make it go away? Yeah, you chew gum or you squeeze your nose and kind of blow down, because what you want to do is you want to push some air up here into your middle ear to equalize the pressure. When the pressure isn't equalized, your eardrum gets pushed one way or the other, okay?
The same thing during diving.
Same thing if you go diving. I remember when I was taking scuba lessons, we had a rope from the boat up there, and you literally would go down every foot, and you would have to go, you'd go down another foot, and you had to, because your ears started hurting really quick as the pressure changed. And I'll bet I had to clear my ears 20 times, going down to 45 feet maybe. So yeah, and this tube right here, this eustachian tube or auditory tube, this is the problem in kids. And the reason kids get so many ear infections is because this tube is smaller and it's shorter in their, because of their anatomy. And the slightest little bit of inflammation causes it to block off. And once it blocks off, then this cavity in here fills with pus, and that's called otitis media. And you go to the doctor, and the doctor looks in the baby's ears and says, oh, your kid's got an ear infection. Here, take these antibiotics. And the antibiotics clear it up. But the whole reason for that infection occurring is because it couldn't drain itself out. And our body does fine with infections most everywhere as long as we can drain them. So there you go. So, external ear up to the drum. Internal ear, middle ear contains the 3 ossicles and connects to the nasopharynx. And now we're going into the inner ear, which is this conglomeration of stuff here. And just for your information, this part of the ear is called the cochlea. Looks like a conch shell. The cochlea is where you're going to hear from. Okay? This is what you hear with. And you've heard of people getting cochlear implants. That's because this part doesn't work on them anymore. And the other part of your inner ear, which is just as important to you really, is this collection of stuff right here. It's called the vestibule and the semicircular canals. These are the things that make us get dizzy when we ride crazy rides. It also, without keeping my eyes open, I can tell you that I'm bending over forward, and I can tell you that I'm upright because it has sensations in there that tell you which way gravity is pulling on you and so forth. This is also the part of your ear that tells you when you're riding in the front seat of a car and you go forward and you're accelerating, you feel that. You feel acceleration, and you feel deceleration when you slam on the brakes. So this is your equilibrium. So this is your vestibular apparatus. So this is your vestibular apparatus here. This is your cochlea here. And notice this is the vestibulocochlear nerve, which is cranial nerve 8, which we used to call the acoustic nerve. But notice it really should be called the vestibulocochlear because it has 2 parts. This nerve collection here comes from the vestibule. This collection of nerves comes from the cochlea. So this is the part that you hear with. This is the part that gives you equilibrium. And the other kind of weird thing in this picture is there's another nerve running through here, which is called the facial nerve. Yeah. What does the facial nerve do? Facial muscles of facial expression.
So if you can wiggle your ears, is that your facial nerve?
What?
If you can wiggle your ears, is that your facial nerve?
Yeah.
Is that true about the bug?